Hello, my name is Caleb, and this is Lab 5, Falling Slinky. The purpose of this lab is to predict the motion of a falling slinky and analyze the effects of its surroundings. I use GlowScript for the computational model to predict/graph the object's position, and I use Tracker as the software to track the observed position. Some of the fundamental principles include Newton's second law, which relates the net interaction between a system and its surroundings to the observed motion of the system. The drag force, which is the resistance caused by the motion of a body through a fluid like air, and the gravitational/slinky force. Slinky force is just the tension and is opposite to gravitational force. Some important formulas include the formula for drag force, the formula for net force, the formula for momentum, the velocity update formula, and the position update formula. This slide contains the observed motion of the slinky as it was falling. As you can see through the Y graph of the slinky, for most of the video, the slinky did not change position, or the bottom of the slinky did not change position until we started getting closer to the end of the video where the top of the slinky reached the bottom of the slinky and it began to fall. This slide contains the GlowScript code used for the computational model. It includes the initial conditions, the mass, the position, the velocity, the time, the change in time, the gravitational constant, the unit vector for the y-axis, and the drag proportionality constant. The first while loop contains the code for while the slinky remains stationary, or while the bottom of the slinky remains stationary. It includes calculations for the net force, the position update formula, and the velocity update formula, as well as the change in time. The second while loop contains the code for when the top of the slinky reaches the bottom of the slinky and it begins to fall. This also includes calculations for the net force, the position update formula, and the velocity update formula. This slide contains the results of the computational model compared to the observed model. As you can see, the computational and observed model are very closely related, with only slight differences towards the end of the graph, where there may have just been slight deviations in the choice of the center of mass on Tracker. For the what if and why questions, the why question is, why does the bottom remain stationary? Well, this is because the forces in the y direction cancel out. Although the gravitational force acts downwards, the slinky acts as a big spring and counteracts the force with a tension force of equal and opposite magnitude, causing the bottom to not move until the top reaches. The what if question is, what if we put a large weight at the bottom? Would it still remain stationary? This question, it depends. As long as the slinky is either long enough or has a large enough spring constant so that the tension is equal to the gravitational force, the weight will remain stationary until the top of the spring reaches it. Some possible errors that need to be taken into account is that the observed motion could be experiencing fluctuations due to other external forces that weren't accounted for in the model, and inaccurate placement in Tracker for the point mass of the object could cause deviations as well.